Hello and welcome to the UCal Calibration course lesson 2. This lesson is instrument design. So the focus of this lesson is to discuss how instrument design and technology relates to what we're trying to do. If you think back to lesson 1, we described near-infrared spectroscopy as basically looking at the interaction of near-infrared light at specific wavelengths and determining how that near-infrared light interacted with our sample. So that need drives instrument design. So let's jump in. There are many different technologies that are available for near-infrared analyzers. Some of the ones that are out in the market right now, for example, are filter technology, FT or Fourier transform technologies, various other means like AOTF of determining or separating out wavelengths. We've got diode arrays or photodiode arrays, as well as scanning monochrometers. All of these different designs have similar requirements or similar features. First of all, they've got some sort of a energy source and a wavelength generator. So they can generate near-infrared light across various wavelengths. They've got some ways to discriminate amongst those wavelengths to make sure that when we're making a measurement, we know what wavelength it relates to. That light impinges or interacts with the sample. It's collected by a detector. That detector turns that light into a voltage, into electrical energy, passed along to a single signal processor to evaluate, and then it's stored on our computer. So all NIR analyzers do this in various fashions. So a couple of the technologies that we've got available within KPM, one of which is a filter instrument. It's from Process Sensors, also from SensorTech. In this technology, we've got a light source. The light passes through a filter wheel. These filters are bandpass filters, so they let a segment, a wavelength segment of light pass through. It goes through a slit, interacts with our sample, either in reflectance or transmission, and it's collected by a detector. So as this wheel is spinning, we know at any one position, we know which filter is in place. We can measure the response and the detector, and we can use that to relate the reflectance of the sample at that filter position or that wavelength. Another technology we have within KPM is represented by Unity Scientific and also Chopin Technologies in the Infraneo, is the scanning monochrometer technology. In this technology, we've got a light source. So white light passes through a slit. It impinges on a concave holographic grating. So this grating has got thousands of laser etched lines. You can think of them as tiny prisms. And as this grating moves, the light that is impinging on the grating hits those lines, and it's diffracted into various wavelengths, like a rainbow. So that light reflects off of the grating, and a very narrow segment of wavelengths, very precise segment passes through a slit, interacts with a sample, and is collected by the detectors. So at any exact position of this rotating grating, based on that position, we know the exact wavelength that is passing through the slit and is going to our sample. So as this grating rotates, we can collect the energy and we can collect a full spectrum. So these are the two technologies that are represented within KPM. So on the SpectraStar instruments, we've got all of the essential elements that I just described. Our light source is tungsten halide. Our discrimination is done by a concave holographic grating. It's termed a predispersive because if you remember the last diagram, it is dispersed, the light is dispersed before it hits the sample. So the light that is impinging on the sample is a very narrow segment. It's a fraction of the total energy on the sample. So this is very nice because we don't heat up the sample with white light. We've got various detectors. There are different composition, different types of detectors. We use an InGas detector. We use a very advanced one. It's called dual-cooled InGas. The substrate is made of indium gallium arsenide. So these have a very high sensitivity and they're very high performance detectors. So this is used to take the reflected energy and transform it into a voltage. We make several measurements. We make a dark signal. If you remember the first lecture, we talked about dark signal is when there's no energy that is going through the optical path. So we are measuring the background signal, the electrical noise or dark signal that's passing through all of the electronic circuitry. We look at a reference. In this case, it's a reference paddle that is underneath the sample stage and spectrostar. And then we're looking at our samples. Okay, and we're predispersive. We're various design tricks. These instruments are very high performance, much more high performance, for example, than we even had 20 years ago. So the electronics have gotten so much better. The detector, the amplifiers, the detectors themselves, the wavelength range that we can look at, the encoders, the number of lines, and therefore the resolution that we've got on the encoders and how accurately and repeatably we can determine the encoder position and thus the grading position. All of these have gotten so much better, and it makes our job in using the instrument so much easier recently. Another one that's been implemented by Unity is TAS, and this is a way that we align and normalize the wavelength scale and the energy scale. So as I discussed, the XT uses predispersive optics, so the white light is split prior to the sample. There are other technologies where you have white light impinging directly on the sample. You have to really limit the amount of time that the white light is on the sample because it very rapidly heats the sample and drives off moisture. So in our technique, we can, these samples are exposed to a one wavelength segment at a time. So that means, for example, we can make repeat measurements on our samples without worrying that we're warming up the sample or changing the moisture. So after the impinging on the sample, the light goes directly to the detector. So this also makes for a very efficient design. So we don't need to do any splitting, any fiber optics or anything after impinging on the sample. It's reflected directly into the detector. So one of the key things with a scanning monocrometer is reliably and repeatedly setting up your instrument. If you remember that the grating is rotating, the concave holographic grating is rotating back and forth, and that is sweeping diffracted light through a slit eventually onto our sample. So it's very important that we are aligning our instrument so that we know exactly the positions of that grating that relate to our wavelengths, but also on the y-axis so that we know that the absorbance or the reflected energy is precise and comparable across time and across instruments. So for Unity, we use something we call TAS, or True Absorbance Spectroscopy. It is a proprietary system for maintaining the instrument alignment for the XT. Everybody should know about this from the installation and daily use of the instrument. The objective of TAS is to force the instrument to behave consistently from day one and also according to factory specifications. There are a set of three standards that we use to set up the instrument and then evaluate the absorbance and the wavelength consistency. It makes sure that we are performing, that the XT is performing according to factory specifications. If it ever falls out of alignment or drifts for some reason, these same standards can be used to recalibrate the instrument. And just as a quick note, but we're also looking at the lamp test before each sample run. So we're putting this together. We're scanning these various wavelengths. We're storing them on our computer. And the end result is that we end up with a spectrum. So it's a series of values, of absorbance values at a range of wavelength values. So that is termed a spectrum. So we then use spectra and a calibration process to create models that translate the entire set of absorbance readings into a prediction of our constituent of interest. And that's going to be the subject of our next couple of lectures. Okay. We use a first order, a direct model, so we don't square or cube any terms. So we use the raw data from the instrument to do this. We do some modeling, some data reduction techniques, which will be part of our next lecture to do this. But at the end of this, really what we're doing is we're creating a long linear equation. This is just a long y equals mx plus b equation. So our constituent value equals an offset plus a coefficient times the absorbance at our first data point, our second data point up through all of our data points. And we're going to be using a multidimensional space, but this is directly correlated to wavelengths. So a linear equation from our spectrum. Okay. So the model will calculate all of the B coefficients, the offset, and the coefficients at each wavelength. The instrument provides the absorbances, the A's. And that is a quick summary of our instrument design, what it is doing, how it is taking the light, separating out the wavelengths, impinging that on the sample, measuring it, and providing the raw data that you are going to use to create calibrations. Thank you.